start. So let me just recall two important results that we proved on the real line. One was the Bolzano that every bounded infinite set has a limit point. This was one of the important results that we had. We got this by first looking at intersection of closed intervals jamming in with the diameter going down to 0. The second thing that we got out in which instead of these closed intervals we started taking closed sets jamming down. Okay. So we said that if sets in get a sequence of closed sets which are bounded non-empty such that one Fn plus 1 contain, that is they are non-decreasing, non-increasing. Fn 1 contained in Fn, they are shrinking, then intersection n equal to 1 to infinity Fn is non-empty. Further, if an additional condition that the diameter of the sets converges to 0 as n tends to infinity, that the sets are really shrinking, then the intersection which was non-empty is a singleton. Not only non-empty, it is a single point. Okay. So these are two important results we had on the real line. One is the Bolzano-Weierstrass's property, which asserts that every bounded infinite set must have a limit point. The other one is that if things are closed, things are shrinking, they are nicely bounded and diameter goes down to 0, then the intersection must be a single point. Now, what we have seen this, so let us recall again, what about the, when I say there, that means there is these two results in a general metric space. Everything that we do will be motivated by what we learnt on the time. Okay. So we have to know our real analysis well. So therefore, the question is, we are now going to look at the generalization of these two results in a general metric space now, not necessarily R, and see whether they will be true or false or what adjustments that we have to make. As far as the result 1, this is not necessarily true in a general metric space. we will recall the example that we gave the space. Okay. So, for example, consider the metric space L infinity R. What is L infinity R? Again recall, it is all set of all bounded sequences, and the distance used is the maximum difference in the coordinates. Okay, so let us look at this in this space, in this metric space. Consider the set consisting of sequences where un is the infinite vector which has 0, 0, 0, 1, 0, 0, 0, it's in the nth coordinate. Okay. So, un is the vector which has nth coordinate 1, all others 0. So, you have u1 at the first coordinate 1, all others 0, u2 second coordinate 1, all others 0. Like this we get a sequence of vectors in this. Now, this set S is obviously bounded because the distance between any two of them is 1. So, therefore, the diameter is less than or equal, maximum distance is 1. So, the set is bounded and the set is infinite because for each n S is infinite. Since the distance between any two of them is 1, there is no chance of they having a limit point, because if there is a limit point everybody should go within that neighborhood however small it is, but they refuse to give up that distance 1. So, okay, since any two elements in S are at a distance 1, in fact, this is one thing you should remember, that if we have a set S which where any two elements keep a definite distance away from each other, then there is no chance of them having a limit point. One is only accidental, I could have put half here, still it is the same. Okay. Distance 1, it follows that S does not have a limit point. So, we have an infinite set which is bounded but does not have a limit point, whereas on the real line the moment you had an infinite set which is bounded, it must have a limit point. So, thus we see that Bolzano-Weierstrass property is not in that form in L infinity. Okay. So, we have BWT Bolzano-Weierstrass as stated in 1 does not hold in L infinity. There is a bounded infinite set which does not have a limit point. What is the status of 2 then? Now, as far as the Cantor's intersection property is concerned, again the same example helps us. Let us look at the set S as before in L infinity. Take that same set of all these unit vectors, okay, whatever you want to call them. Take that set. Is that set closed? It does not have any limit point. What is the necessity for closed set? Yeah, it must be equal to its closure. Since it does not have any limit point, that itself is its closure, and therefore equal to S is equal to S closure. Okay. S has no limit points, therefore S closure is equal to S itself. What is S closure? S union all the limit points. There is no limit point. The limit point set is empty, so S union S. And there and S closure is closed. S is closed if and only if S closure is equal to S. Therefore, S is closed. What was I trying to prove? One contained in S. Okay, right. Now, I was thinking of something else. Okay. Now look at S1. S1, you just take this and drop the U1 and take from U2 onwards, which is S minus U1. So just take all the fellows from the U2 onwards. What about that set? That is also closed. Okay. Again, no limit points. So S1 is closed and S1 is contained in S. What is in general Sn? How do I define Sn? Drop the first n fellows and take from the n plus 1 fellow onwards. So S minus U1, U2, again Sn is closed and Sn is contained in Sn minus 1. The previous fellow will have Un also dropped Un minus up to Un minus 1. So what can you say about this sequence of sets now? S1, S2, S3, I can go on getting a sequence of sets. They are all closed and they are one contained in the other. Instead of F, I use the letter S. Sequence of sets Sn, now instead of this metric space in L infinity, Sn plus 1 is contained in Sn, but what is their intersection? Nothing. You go on dropping one by one, nobody is allowed to stay. Okay. So therefore, we have Sn closed sequence, a sequence of non-empty, everybody has something, non-empty closed sets, right? Are they bounded? Because the distance between them is always 1. So closed sets, so closed bounded sets such that 1 Sn plus 1 is contained. But intersection n equal to 1 to infinity Sn is empty. So again the property 2 also does. Therefore, Cantor's intersection property CIP as stated in 2 does not hold in L infinity R. So both these properties flopped when we try to generalize. Now when it succeeds, it is a theorem. If it flops, it opens the door for another theorem. Now yesterday I was watching this great fun about this Higgs boson thing, and in that one of those interviews, the press conferences, the guy asked, the press fellow asked, so if you confirm that it is really the Higgs boson particle, then does it make the standard model complete? Then what do you do? Then he says, then the person said, if it confirms that it is a boson, we are all delighted that we have finally proved that there exists a boson particle and the standard model is correct. If it is not, then we have a lot more work to do. We still go on finding what is missing then. If the standard model is not correct, how do I modify the standard model to make it correct? Okay, so now the standard model failed, so we are going to modify it to correct. So the boson experiment failed here, but failure is the door that opens for something new, success. Okay. Okay, so now that this failure has taken place, we take a step backwards and what the fellow does is goes back and looks at the proof, where I used what, why did that thing fail, whereas this thing failed. If I write the same proof as that for this fellow, which point there was a difficulty, all that you analyze, and what we will do is, we will therefore will not go through all those details. In fact, people should write papers in which their attempts failed. I think they are more useful papers to me than writing a paper in which the first statement is, let the following conditions hold, then this. The whole thing looks like bogus magic. Why should I let this? Why should I let 1, 2, 3, 4, 5, 6, 100 conditions, then some 101 result must be true. So people should write why I needed this condition. If I did not put it, something happened. Explain that. Then you see, okay, this is an essential ingredient required for the result. Okay. So probably one should go back and look at all the proofs I gave for Bolzano-Weierstrass theorem and Cantor's intersection property, and then write the same proof for this L infinity space and for this set, and see where exactly that proof failed. But we are not going to do that, and that's I think that's precisely what the role of a teacher is. You should do that, but at the moment we are in a hurry. Everybody is in a hurry to learn. Okay, so therefore now what I am going to do is, I backtrack and look at boundedness in R from a different point of view. I always wondered, see, we talk about color being made up of 7 frequencies, the Vib Gayar. No, you can do an experiment and show that all the diffraction spectrum and show that the 7 colors there and so on and so forth. How do you convince how do you convince a man who is color blind? So what are you talking about? I am seeing only white color. I can see only white and black. You can never convince him. So what does that mean? Does it mean this fellow is lying or that fellow is lying? The color blind fellow says this guy is all lying. He is simply showing some experiment and saying that there are 7 colors. I don't see any 7 colors. But that fellow says, he is saying only black and white, I am showing him 7 colors and he is not listening. Now who is right? Philosophically speaking, it is in the perception of the person who is seeing it. Okay, so the whole business of science is, how does one perceive nature? Okay. And I think that is where the interaction with mathematics comes. Mathematics is a subject which is created in the mind. He does not bother about anything. He creates a certain symbols, creates a rules. This is the abstract mathematics, the purest of pure mathematician. So it is a game he plays in the mind. If it is a game he is playing in the mind, it is the same mind it is perceiving the nature. So therefore some interaction is taking place in the mind. This fellow is saying, hey, use me, you will get the answer. So therefore there is this mind game that is going on. And it is therefore, it is very difficult to dismiss whether something is right or something is wrong. Something is right for the person who is seeing it right, and it is wrong for the person who is not able to see it from his viewpoint. So therefore, I think it is extremely difficult to say at what point of time science has found something absolutely right. Okay, so it is very, very difficult to say, and therefore to understand the other person's viewpoint, you must learn to look at nature or any point, any proof from different points of view, any concept from different points of view. So therefore, when you write a proof, is there another way of writing this proof? Is there another way of looking at this proof? So the more ways you look at it, the broader your perspective becomes. So therefore, now we are going to look at this boundedness from a different perspective, a different point of view. Okay. So now even now, if these guys say that I have found the boson, Higgs boson, I say, how do I know? You are going to throw at me a number of data, a huge collection of data that you collected, and a huge collection of calculations that are done all over the world. Every bit of it I must trust, and then say, yes, it is true. You may say, why are you not trusting? I remember there was a very major problem which was resolved in the 1970s, which was called the 4-color problem. I think many of you would have heard of it. How you color a planar graph with just 4 colors, okay, so that no 2 adjacent countries have the same color. Then minimum number of colors required is 4. This is the famous 4-color problem, which remained unsolved for a long time. So somewhere in the 1970s, somebody from Illinois, I think, Apple, he proved it, he and another colleague of his. The proof was as follows. He did some mathematics, and when he did some mathematics and classified that there are certain n types of such maps, okay, all planar maps, I can classify them to some 72 or 75 or some finite number of categories. And then he used a computer to generate coloring for each one of these categories and said, look, I have got the coloring for now all categories, and therefore I can color all maps with 4 colors. While doing so, he found certain logical errors in the IBM computer itself, which we had to correct first. Because he was a mathematician, he was quick to jump to see that there is some error going on here. This fellow is doing something wrong. So even the IBM computer was non-trustable. Okay, so one has to view things very detached until we are very sure that that is sure. Okay, and I am not sure when we can say it is very sure. Okay, that confusion exists. Anyway, as far as mathematics is concerned, we are a little better off than the physicists. Okay, we put a QED at the end, which means don't ask me any more questions. It's over. Okay. If you have seen many pure mathematics books, at the end of a theorem, when the proof is over, they would have put a thick black square, which simply means the proof is over. If you have not realized it, go back and read it again. Okay, that's what it means. They used to put QED in the past. Okay, many times you don't realize the way they write. Okay, therefore they put that block. Right. So yeah, I allowed to have dig at my own community. Anyway, so now I am going to look at this boundedness from a different point of view. What does boundedness mean? I say a set in the real line is bounded if there is a big interval in which I can completely capture that set. So in other words, you say you give me big enough suitcase, give me a big enough suitcase, then I can pack all the elements of the set in that suitcase. Okay, you say that I you give me a 100-inch suitcase, I can put all the elements in that set and that suitcase, so it's bounded. Fine, but when you go to a market to buy a 100-inch suitcase, it is not available. He says only 10-inch suitcases are there. Now I don't know. I have to come and see whether I can pack the thing in 10-inch suitcases. Now when I say that when I can pack these things in 10-inch suitcases, I don't want to buy infinite number of 10-inch suitcases. I lose all my money and then nothing left to pack. Okay, all my money is gone. Whatever I would have to buy infinite number of suitcases. So I want to buy finite number of 10-inch suitcases inside which I can pack this set. But then I go to market, maybe there is no 10-inch suitcase, there are only 2-inch suitcases. He didn't have enough number of them. He said, however many you want, I will give you 2-inch suitcases. I should still be able to find finite number of 2-inch suitcases in which I can pack it. So, in other words, whatever size you give suitcase, I must be able to buy a finite number of that size suitcase and pack the set. Yes, that's a better, that type of set I like because it is manageable. Okay, it is highly manageable. See, in the good old days, there was, I don't think any of you would have seen it. If it is in your house, go and see in the attic somewhere, it may be there, your mother or grandmother would have stored it, or whatever it is. It was called hold all. Has anybody seen a hold all? Yes. It was a very peculiar thing. Basically, it was a hold all. You could put everything in it and pack. Your clothes, your bedding, your pillow, and your shoes, your chapel, and all that eatables that your mother gave you to take in the train, which would take 3.5 days to reach from Bangalore to Delhi, and anything and everything you pack in it. Okay. So that sort of convenience is what I want. I take one suitcase, one holder like that and dump it. So, or I should have smaller pieces, but only finite number of them. So that is what I am going to look for. Okay. So now suppose S is bounded. So suppose I have a bounded set in R. I am going to see whether it is possible to pack it in such suitcases. So what I do is, I decide on, take any size So I am not going to write zero size. These days all film actors are talking about zero size. I am not talking about zero size, positive size. Okay, take R greater than 0. Now I am going to see whether I can pack this set in R size suitcases, finite number of them. When I say suitcase, I mean open balls. That is what I mean. In the real line, they are open intervals. I will use the terminology balls only. Okay. So now I will go and buy one. Okay. So let me consider a BRX, X real number. Okay. So I bought one suitcase of size R. The possibilities are, I am lucky, I am able to pack S in this, or I am not lucky, I am not able to pack S in this. So there are two possibilities. Right, like this. The first possibility is, I will put it even this side, S is in the NBRX. Great. So one suitcase is good enough for me to pack. Or the other thing, possibility is, S is not in BRX. If S is not in BRX, somebody from S must be lying outside BRX. So there exists an X1, therefore there exists an X1 in S outside BRX. Right? So let us draw a small picture here. So here is x, that is R, and where will x1 be? He will be sitting either on the, because the distance, this BRX is all the fellows inside. This fellow is, that means either on the boundary or sitting outside. So x is somewhere there, x1, and the distance between x1 and x will be greater than or equal to R. Possibly it may be equal to R also, because consists of only those which are less than R. So the remaining is greater than or equal to R. So there must be such a point. So either I have already packed it in one suitcase, or there is some item left which I could not pack in this suitcase. Then what I do, I go buy a suitcase for this fellow, okay, with this as a center. So then look at BRX1, right? Now I am going to look at a suitcase of radius R about it, right? Now again two possibilities. S is contained within these two suitcases, or S is not contained even if I pack in both the suitcases, right? Now what happens? Again in this case, there must be one more fellow staying outside both these suitcases. If I am not able to pack S in these two suitcases, there must be a chap sitting outside both these suitcases. So there exists an x2 belonging to S minus BRX union BRX1. What do? Now this is the x3. I now consider this picture, I will transfer here. I now consider, so look at BRX2. Now what will happen? Again, I am able to pack S in these three suitcases, or I am not able to pack S in these three suitcases. So either S is contained in BRX union BRX1 union BRX2, or S is not contained there. BRX union BRX1 union. Right? Now, either this process has to terminate at some stage, or it will continue indefinitely, right? So, either this process terminates, okay, this is one, terminates after a finite number. Say that number will depend on the radius I chose, a finite number n or steps, or continues indefinitely. Huh? I didn't get it. Huh? Yes. Yeah, it will not be a function of x, it will be a function of the set S. X is only an arbitrary point I chose. Yeah, that's okay. If you want to put it, but that's not my criterion. The fact is the number S is not okay. You could have started with any point X. Okay, so that's not. I am not going to worry about it because that's very arbitrary. This is this. What it says is finally what is the conclusion? I would have chosen this as the first set or that as the first ball. Either way, I would have got the same thing. with that the same NR I would get x1, or because again you would have to write x, x1, x2, x3. It depends on the next thing I wrote and all. I am interested only in the number, that is the number of steps that it takes. Okay. Now, there are two possibilities, therefore, this process is going to terminate after a finite number of steps, or it is going to go on. If it is going to go on, I am in trouble. I have to buy an infinite number of suitcases. So, I will have to make sure that the second one does not take place, or if it takes place, then bounded sets are not that great, okay, as we think. Right. So, therefore, now what happens in case 1, what do we get? If the process terminates after a finite number of steps, that means I will get a finite number of open balls whose union will contain S. So, in case 1, there exists a finite number of open balls of radius r such that their union contains S. That is what happens in the first case. Now, let us see what will happen in the second case. In case 2, what have I got? Look at that x1, x2, x3, where are they coming from? They are all in the set S, because remember there is an x1 in S which is outside, there is an x2 in S which is outside that. Initially the x I chose may not be in S, but after the argument showed that this x1, x2, etc. are all in S. So, we get, and where are they same or different? Each one is different. If you have x1, the x2 lies outside that circle. So x1, we get an infinite sequence of elements S1, S2, etc. such that what is the distance between any two of them? Everybody lies outside the other. So, that will be greater than or equal to r. If you take the third stage, I got x1, x2, x2 is outside this circle, the x3 will be outside both the circles. So, that distance will be more than r, that distance will be more than r. So, any two of them will have a minimum distance of r from each other. So, now look at this set S1. S1 is this set for me, S1, S2, Sn, etc. Is this an infinite set? All these elements are distinct. Oh, I am sorry, should I put xi or si? Xi, xj. All these elements are distinct, and therefore this is an infinite set. So, this is an infinite set, and this is a subset of S, and S itself is bounded. So, any subset will also be bounded. So, S1 is contained in the bounded set S, and therefore S is bounded, S1 is bounded. Now, S1 is a bounded infinite set in the real line. Bolzano-Weierstrass property says it must have a limit point. So, S1 is a bounded infinite set in R, and therefore, Bolzano-Weierstrass implies S1 has limit point. Okay? But on the other hand, Dispuller says any two of them keep a positive distance of R. There is no chance that they have. When I just now mentioned, when the fellows decide to stay away from each other, minimum R distance, there is no chance of their coming close to each other. Okay? But star implies S1 has no limit point. So, therefore, we get a contradiction. So, 2 cannot be true. In case 2, we get a contradiction, and therefore 2 is false. Therefore, 2 leads to a contradiction, and hence is not true. So, therefore, this is ruled out. This is the only thing that will happen. The process will have to terminate after a finite number. So, what does that mean? Give any R greater than 0, there are a finite number of R balls which will cover the set S. Conclusion is, therefore, let us write down the conclusion. S is bounded in R implies for every R positive there exists a finite number of open balls of radius R such that their union contains S. This is what we have finally concluded. So, in the real line, boundedness is a nice thing that however small packets you give me, I can pack with a finite number of that size packets the whole set S. Okay, is that clear? Our great friend, that example which keep getting at L infinity, says this will not be necessarily true in general metric space. This is not necessarily true in a general metric space. For example, in L infinity R, the set S equal to UN. What is that? Same UNs that I stated last time. UN has the nth component 1, all others 0. Same notation as the previous example. The set n UN is bounded but cannot be packed in a finite number of open balls of radius 1 by 3. Why? In any open ball of radius 1 by 3, only one fellow can sit, because the distance between any two of them is 1. Okay? So, therefore, you need an infinite number of 1 by 3 balls to cover that set. Okay. So, therefore, For example, if there are two human, quote unquote human beings, one born in L infinity space and one born in the real line meet. And this real line fellow, bounded is same as that here, you can cover it by finding. Hey, that fellow says, no, that's not true. But he is seeing in his world and you are seeing in your world. So therefore, the perception was different. In the perception in the real line is the boundedness perception and this finite number of any size balls is same. Whereas that perception is not true, it is totally different in a general metric space. So therefore, we will have to give two different types of names for these two types of properties. This is one property, boundedness is one property, they are synonymous in the real world, they are not synonymous in a general metric space. Their dictionary is totally different. Okay. So therefore, we give a different name for that property and then say the real line, somebody has this boundedness property if and only if he has that property. Later we will see that. Okay. So therefore, therefore we give the following definition. Who knows, tomorrow we may meet a person from Mars whose world is an L infinity. You say, what are you doing? Everything you are doing is false. This is not correct. Okay. No, that is why. See, about days back, there was a very important event that was celebrated. Of course, that was 23rd June. What was it? Alan Turing's birth centenary. And before that, Alan Turing, one of the greatest things that he did was finish half the job that Gödel left unfinished. Hilbert had a great dream that everything basically can be axiomatized. And Gödel showed that no, that's not true. There is something called an incompleteness theorem. Okay, there is a famous Gödel's incompleteness theorem. And Gödel, that was Gödel's PhD thesis. And 2 years before that, Gödel wrote another thesis for his master's. It was called the completeness theorem. Okay, it is something else to show that the first order predicate logic is good enough to verify all the arithmetical theorems. Okay, anything that is true can be found if you have the first order predicate logic. The second incompleteness theorem was to show that if you have an axiomatic system rich enough to include arithmetic, then you can make statements which can be neither proved nor disproved. This is something like this. I am not telling it in precise language. Roughly this. That's what he called as incompleteness theorems. By the way, one of the examiners apparently told this theorem, this thesis is just like the MSc thesis. We should not give the degree for Gödel. But however, there are others who are sensible who gave him the degree, and later we know, how important that result was in logic. Okay. There is simultaneously, along with this dream of axiomatization, Hilbert raised another question that given any problem, there must be a process of deciding finally that this is the answer. Of course, what he had in mind was an algorithm. An algorithm means finite step, which essentially means to construct a halting Turing machine. Okay. And Turing raised this problem of undecidability, and thereby Hilbert's both dreams were shattered. Okay. The man who set the agenda for the 20th century mathematics was a shattered man, okay, when both these dreams were destroyed. I don't know why. So therefore, what I say is, it is all very difficult to say which is true, which is not true. even according to Gödel, in your own world, you live in a particular system which is consistent, then you will always find certain things which you could neither prove as true nor disprove as false. That will remain as. So therefore, there is no hope of finding all the absolute truths. There are certain things which may be true, which may not be true, which are neither true, which are neither false. Therefore, you have to expand your systems. You believe that? Then go ahead with that. You believe this? Go ahead with this. You can have set theory with continuum hypothesis. We can have set theory without continuum hypothesis. Okay. What Gödel showed was that set theory, the Zermelo-Fraenkel axiom, will still remain consistent if you add continuum hypothesis to it to be valid. But what he was not able to show was that Zermelo-Fraenkel axiom set theory will remain valid if continuum hypothesis negation is included in it. And subsequently, a few years later, Cohen showed that that is also true. So, Zermelo-Fraenkel continuum true, Zermelo-Fraenkel not continuum is also true. So therefore, who is right? Both are right. That is precisely what I said, that it is in the view, in the perception. If you want to view it from the perception of continuum hypothesis, you can go ahead. You a doubt master, say I don't like this continuum hypothesis, you can still do valid mathematics. Okay. So therefore, we give a definition, we give a terminology. This terminology, whenever you are in trouble, we do a namakaranam. Okay. Definition, yeah? Yeah. No, I only said S is bounded. Okay. If S is bounded, in R, there exists a finite number of open, for every R, there exists a finite number of R balls which cover that, which contain that. What you have in mind is different. You know what you have in mind. Okay. I did somewhere I can find. Somewhere I can find R such suitcases. Maybe one suitcase I will find in Commercial Street, one in Malleshwaram, one in Brigade Road or something like that. But you can't say I want all of them from this shop. That's what you have in mind. Okay, so there is a difference between that. Okay. So now what is the definition that I am going to give? I already have the notion of boundedness in a metric space. What is meant by boundedness in a metric space? If the set is bounded, if the maximum distance between any 2 points is under control, that is less than or equal to k. So now I am going to give a new notion, namely in a metric space X, a subset S is said to be totally bounded if for every R greater than 0 there exists a finite number of open balls of radius R such that their union contains S. Deliberately writing it in words, not in symbols, so that it sinks what it means. Okay. Now for a creature which lives in the real line, the word bounded and the word total bounded would mean same. For a creature living in the L infinity space, these two mean different things. Okay. So therefore, what we have so far seen, is 1 in R, S bounded implies S totally bounded. In general metric space, S bounded need not imply S totally bounded. I am not saying it should not imply, it need not imply. Some cases it may, like in the real line, in some other metric spaces it may. So it does not imply that S is totally bounded. So in general, these are two different concepts. However, take a metric space. Consider any metric space X rho, a general metric space. Suppose I have a set S and S is totally bounded. I will write TB. S is totally bounded. So I am now looking at a general metric space. I have a totally bounded set. Now what does total bounded set means? Oh my God. Whatever size suitcases I give, I will be able to get finite number of them to fill it up. So therefore I will choose a standard size suitcase, because that is what is the aircraft say. So I am going to buy a 1-inch suitcases. Okay. So for R equal to 1, we must have a finite number of radius 1 open balls that contain yes, that means their union contains yes. So there are finite number, so let this be, say B, the radius is 1, so and let the center be S1 or not X1, B2, X2 and say Bn1, X, I do not know how many of them will be there, so I will call it Xn1, depends on 1, the radius 1. So given that radius, there are going to be a finite number of balls and union B1xj, j equal to 1 to n1 contains S. Okay. For every radius we can do it because it is totally bounded. So in particular I can do it for 1. Is that okay? So now what does that mean? These are all they may be intersecting, they may not be intersecting and so on and so forth. There are finite number of them. Now take any 2 points in that set S. Take any 2 points in that set. Now, since this union covers S, this fellow must be in one of these balls. So therefore there exists, I will call it an xi1 such b1 xi1 such that x belongs to b1 xi1. Okay, one of these balls will contain x, and also b1 xi2 such that y belongs to b1 xi2. They need not belong to the same open ball. One of them will belong to some to the other thing, and therefore I will now isolate these 2 balls. Okay, let us now look at these 2 open balls. This is xi1 and radius is 1, x is sitting there. This is xi2, radius is 1, y is sitting there. Okay. Now what can I say about the distance between x and y? I will first take this distance and then go to this distance and go to that distance. Why? Right? So instead of go, that is from here to here is less than or equal to here to similarly there. Okay, that is the triangular inequality. Going from one place directly is less than or equal to going through intermediate places. Okay. Now what can I say about rho of xi1? X is in this ball, the radius is 1, so that will be less than 1 plus rho xi1 xi2. What can I say about this? xi2 is the center, radius is 1, y is inside, so the distance will be less than 1. So therefore, we have got rho xy is less than 2 plus rho xi1 xi2. What are these xi1 xi2s? They are the centers of these suitcases. How many such centers are there? Finite number. Take the distance between every pair of these centers, will be finite, take the maximum. Okay. So this is less than or equal to 2 plus k, where k is the maximum of rho xi xj, 1 less than or equal to I less j less than or equal to n1. Okay, all these centers should possible distances and look at the maximum. So the any two of them will be less than or equal to maximum. So what is the final conclusion? Okay. If you take any 2 points in xy in S, the distance will be at most k plus 2. So the set S must be, what can you say about the set S? The distance between any 2 points is less than or equal to some k1. Therefore, it must be a bounded set. Okay. So therefore, for every xy in S, rho xy is less than or equal to k1. I will call this number as k1. Therefore, S is bounded. So therefore, the conclusion is, if you started with totally bounded, you are sure to end up with bounded, whereas the other way it was not true. Okay. So in other words, there is total boundedness, and this boundedness in Bangalore there was a two-way traffic. You can go this way, also this way. But in the L infinity world, it's a one-way street. You can go from total bounded to bounded, but you can't go from bounded to a total bounded. So therefore, in any metric space, conclusion, X row metric space S totally bounded implies S bounded. So we combine with our earlier result, hence in R, S is bounded if and only if S is totally bounded, because we have seen this way, we are now seeing this way. But in general metric space, only this we can conclude. The other one may or may not be true. S is totally bounded, it must necessarily be bounded, but the converse may not be in general true. So the Weismann from L infinity comes and tells me, look, you state Bolzano-Weierstrass system that Cantor's intersection property, and you very loosely use the word bounded, because for you bounded and totally bounded means the same. Probably you should have used correctly the word totally bounded, because that seems to be a more powerful hypothesis. So he says, is it true that if I now take a metric space and you said that in R every bounded infinite set has a limit point. Now I will ask, in a metric space every totally bounded infinite set has a, is it true or not? I do not know, I am just asking and modifying your question. Similarly, the Cantor's intersection property, you said that in R, if there is a sequence of non-empty closed bounded sets coming down, intersection should be non-empty. Now I will say non-empty closed totally bounded sets coming down non-empty. Is it true? Okay, and that is the investigation. Then when this wise man investigates, he realizes that this fellow is in your world. He simply wrote R, but he didn't tell me that the very powerful property that R is complete. Okay, so that you are using. So therefore, let me make these statements. Hence, we can restate any result about bounded sets in R as results for totally bounded sets in R. Okay, because both are same, and therefore we can have the Bolzano-Weierstrass's property. Every infinite totally bounded set in R has an limit point, right? That is how we can now state Bolzano-Weierstrass's property. These are very fundamental results in analysis. Okay? You just can't do analysis without these results. Therefore, you must understand where these hypotheses come. And the second one is the Cantor's intersection property. What does the Cantor's intersection property say? If Fn is a sequence of non-empty closed, now bounded I will write as totally bounded sets in R such that 1 Fn plus 1 is contained in Fn, then intersection Fn is not empty, and further if the diameter of Fn tends to 0, then intersection of these Fn's is a singleton. These are now the two fundamental results which I started as recall at the beginning of this class have now been restated in view of the fact that boundedness and total boundedness have been found to be synonymous on the real line. Now therefore we ask, are these true if we now replace R by any metric space? Obviously false, obviously still not over the hill. Take for example the Bolzano-Weierstrass. Take the rational numbers as your metric space, not all the real numbers. Take the rational numbers as your metric space, and I know there is a sequence which converges to root 2. So take only the members of that sequence. That is a sequence in the rational numbers. It is an infinite set. It is bounded, but it does not have a limit point because that limit point root 2 is outside Q. So therefore still there is problem. and that problem came because that limit point was outside Q. So, how do I avoid the limit point being outside Q? Make the space complete, and that is what the strong point of R. R is a complete metric space. So, therefore, so let me just write clearly, that is what I meant. Clearly, PW, for example, is not true in the rational number metric space, and it is because of this we had to create the real numbers. Okay. So, therefore, we still have to modify. So, the modified questions are, so we further modify and then we ask Balzan if X row is a complete metric space and yes, then S bounded infinite set implies S as a limit point. And then Cantor's intersection property. If Fn is a sequence of closed, non-empty, closed, what did I say? Totally bounded infinites. Okay. Closed, totally bounded, what else? Set such that 1 Fn plus 1 contained in Fn implies intersection 1 to infinity Fn is non-empty. Further, if dFn tends to 0, then intersection Fn is a singleton. We ask, are these true? And the answer is yes, they are true. Okay. Be true. So, that is how Bolzano-Weierstrass property and the Cantor's intersection property have to be looked at in the case of metric spaces in general. Okay. The completeness is one thing, which tries to make sure that you do not have to go out of this world, and this total boundedness is one thing to say that the set is under nice control of features. They are not just flying away like mad. They are within a bound, but even within the bound they are not flying away too much. So, therefore, they are controllable finite number of open balls any size. Okay. So, this total boundedness, completeness, we are not seen now. One property called completeness, we saw separability, then all the Bolzano-Weierstrass theorem, etc., hinge on the total boundedness property. These are very important properties. I will, I don't know whether I should try to even prove these things. So, like, what I will suggest now is, with all the mess that I have created, which was supposed to clarify the matter of total boundedness, and I hope I have not confused you more than clarified. I used to have, when I was a graduate student in Purdue, I used to teach. It's not like India where you just get 15,000 rupees scholarship to stay in the hostel, food is served in the mess, and you complain if water is not in the tap, the plate is not clean, and so on and so forth. There you have to work to earn your money, you got to clean your apartment yourself, make your own food, and so otherwise go and pay through your nose in the canteen, and so on and so forth. Okay. So I used to teach. Okay, that's beside the point. I used to teach, and I always used to choose the class which started at 7:30 in the morning. The reason was that I could finish by 8:30, or if it is a 1.5 hour class, by 9 o'clock, and I have the rest of the day for my other research and my own courses and things like that. So I had a student in my class, and I never saw him in the class. He never come to the class. The first test, guy wrote the test, got almost something like 98 or 99 out of 100. Very frequent test. Second test, got 100 almost out of 100. Then I went to the chairman of the department and said, look, I am new to this place. I don't see this guy in the class, but he seems to be doing very well in the test. I don't know whether he is sending some proxy and getting these things done, or whether he is really the genuine fellow who writes. Then he said that, why don't you ask this guy to meet you? I said, okay, I announced in the next class that I want to meet this guy, because he is not there to tell. So some of my friends told him. There it's very difficult to find somebody who knows the other guy. They don't talk with each other. Anyway, the guy came to me and I said, are you you? The one you are supposed. Then he showed me his ID and all these things. And then I asked him, why is it that you don't come to class, but you seem to be doing very well? He said, I work. And unfortunately, my work gets over at 8 o'clock. And I am not able to come to the class. And I cannot afford to give up that work. But am I doing bad in the course? He said, no. You are not, in fact, you are doing very well. And I think you should stay out of my class. Because your mind is very clear and you are writing your answers properly. Probably if you come to my class, you will get confused. So don't come to my class, keep it up, and every time I will check your ID. That is the only thing. Don't get annoyed. Okay. So sometimes we try to explain. In the process, we confuse more. Okay. So I hope this total boundedness has not totally confused you. Okay. So what I suggest is, try to write the proofs of these two theorems yourself. Try now, go back and see what you did in the real line to prove Bolzano-Weierstrass theorem. Now, to prove Bolzano-Weierstrass theorem in the real line, you took closed intervals and all that. Now we are in trouble. There is nothing like a closed interval in a metric space, because there is no order. In the real line, there is an order. A less than or equal to x less than or equal to p. There is a closed interval where there is no general order in a metric space. So there itself we are stuck. So now we have to see what should I do to show that an infinite set has a limit point. Okay. So therefore, the only thing is under your control is, previously in the real line you had bounded, and because of bounded, immediately you thought of enclosing it in a closed interval. Now you have total bounded. The only thing that you know for total bounded is, for any radius you have a finite number of such open balls. How do you exploit that? Okay. Remember, for any radius, so you can go on shrinking the radius, and that's the key. When you go on shrinking the radius, finally you will end up with a sequence which will converge, and that will be the limit point. And that converge limit will be there because it is complete. That will make it limit point. And once you have that, remember we proved Cantor's intersection property using Bolzano-Weierstrass theorem, so that will fall off immediately. So the key to this is, how do I use total boundedness in these situations and shrink those open balls to get this. Okay. But these two results are real crucial, true results. Okay, so now next topic that I will start, not today, is now use all these things, is the notion of compactness, one of the most important notions in analysis. Okay. All these ideas are crucial. They are at the foundations of analysis, doing analysis, whether it is separability, whether it is completeness, whether it is boundedness, total boundedness, closed, open, all these are very fundamental ideas. So, the next thing I will do is about compactness, and then we will see the connection between compactness, closed, bounded, totally bounded, and so on and so forth, and we will see that there is a lot of interplay between all these fellows. Then continuous functions, okay, and really we start functions, and functionals are special types of functions, and therefore we will be beginning functional analysis. Okay. By the way, tomorrow I understand there is a major power shutdown, so he will have a problem videotaping the records, the class. So I thought that since he has done it for all the classes, let's not miss one. So instead of Friday, we'll meet Tuesday. Is that okay with everybody? So next week we'll meet Tuesday, Wednesday, and see how you feel, whether we still meet Friday or not. But definitely we'll meet on Tuesday at 3:30 and Wednesday. Is that okay for you? Tuesday? Yeah. Okay. So Tuesday, Wednesday, 3:30 next week.